It was like a brand. They were called Trapper Keepers, and then they had different. I don't think they make underoos anymore, do they? You've never heard of that? I mean, it's like kids' underwear, you know, which is like a creepy thing to talk about in class. But like you would get like the Incredible Hulk underoos, and it was like underwear and a shirt, you know, like that's what you wore when you're running around the house. Like when I was 4, I don't think they make those anymore because I've looked. No, for me. Were you on the stream the other night?
No, I didn't.
Mr. Gonzalez was on the stream. Yeah. I think I'm gonna start doing it regularly.
If you do it again,
I think people had fun. I did one today. I think people had a good time with it. And I think I'll get better at doing it. So I'm already recording.
Did you embarrass yourself or did it go well?
At the end, I was starting to go on a little losing streak, but I think overall, I think I had like a 65% win rate or something. Earlier today, I had an 86% win rate. I was just mowing. Okay, so let's see. We didn't have homework for today, right? Okay, good. So we talked about this idea of shared global namespace. I think I said that maybe look ahead into drivers in Linux. Is that kind of what I maybe mentioned at the end of class to start thinking about? And we're going to look at some code related to that today. Why is my phone blowing up? Okay. Let's see. So we started looking at the idea of creating simple modules. We're initially going to be creating a module out of for a driver. We're actually going to look at some source code for that today. I'm hoping to actually write some of it on Friday, let's say ish. Ideally, I'd like you to be able to follow along with VM. And we just got it working yesterday. Blade's finishing up where you can actually access it from other things. So let's hope for Friday. I think we're close. But in any case, we'll be able to look at some source code and stuff like that here. So remember, the idea of a module is something that we can plug into a microkernel after the fact. So that microkernel is the core operating system kernel, and then we might want to have things, you know, bolted onto it after the fact without having to recompile the whole thing. So Linux, and among other operating systems, have a modular type of interface that allow us to, you know, as long as we have a piece of software that's compatible with how the module works, their module system works, we can write the software and plug it in. And part of that compatibility, I think I probably referenced this, is similar to interfaces in Java. Part of that compatibility says, hey, you have to write these couple of functions. They need to follow this exact pattern. And if you do that, then technically, I mean, it might be logically incorrect, but you are at least syntactically compatible with what the kernel is going to do. When you tell it to register your module, it's going to try to call your init function. And when you deregister your module, it's going to call your exit function that should do any cleanup or something like that. So it's very important that we follow this pattern. So in this example over here, we created our own little, you know, this is our my init function and our my exit function, but then we used the module system. So this is Linux module. So it's the Linux API that allows you to interface with their microkernel module. All right, and it comes with, among other things, a couple of functions. It has a module init function where you pass it your init function. It has a module exit function where you pass it your exit function. That's your way of registering your module with the operating system. All right. And I think that's what we were talking about here in the difference between streaming things one character at a time versus kind of a parallel computing thing where you stream it blocks at a time, and we'll see examples of that. Okay, I think we probably finished up our discussion on this slide, and we may have glanced at this, specifically the top part, I think. But let's kind of start there. I'm going to go back to the previous slide here. So device files are usually stored in our /dev folder. I think I showed you in the dev folder last time. There's like a, SDA1, SDA2, things like that. So everything in a POSIX-based operating system is a file. All our devices are represented through a file. And Linux is a POSIX-based operating system, so is the Mac OS. These files facilitate interaction between user space and the kernel code. Because remember, from our picture back here, we have this area where our user applications are allowed to live, and they have, a much more open security mechanism governing them. And then we have this area over here that's much more protected. Now, our modules do get loaded into kernel space, which means then we have this conflict where it's entirely possible that our user programs might want to use a driver, right? Real life, you launch a video game, you expect to be able to, that video game to be able to take advantage of your NVIDIA graphics driver, right? Well, the video game's probably running in user space. It's not a kernel module, right? You don't install it into the kernel. It's something that runs on top of the operating system. So there needs to be some communication mechanism to cross between kernel space and user space. Let's see. To make the kernel receive anything, you can just write it to the device file. So the device file is the way that a particular device is exposed to user space. All right, so /dev is something that user applications can see, and that's your mechanism by which you can talk to the actual loaded module inside of the kernel, okay, by way of this file. Okay, so to make the kernel receive anything, you just write it to the device file to pass it to the module serving this file. Anything that's read from the device file originates from the module serving it. So if you want to talk to the module, you write to the file. If you're expecting the module to give something to you, you read from the file. Make sense? The file is your conduit, communication channel to your actual physical devices. When we talked about these two groups, so we have two groups of device files: character files. These are non-buffered files that allow you to read and write data character by character. And that's kind of the one I talked about this as being like serial communication. So if you've ever done anything with like socket programming, where and we'll do some socket programming stuff in here, but if you've seen that before, where you open up a communication channel over the internet, typically you're reading and writing to it by byte, a character at a time, typically in the C language. Let me go this. Let's do it right after this slide. Size of a char. So let's call it character here, because they're referring to this thing as a character stream, writing to and from this file. How big is a character? Okay. Why is it 1 byte? Okay. Did we talk about this in here already? Okay. So a character is 1 byte. System maps to ASCII. So we read/write data 1 byte at a time to character dev files. Where buffered files, you can kind of load stuff up onto it, writing it in chunks at a time. All right, so let's go here. All right, so in driver code, when we register a character device, so we're talking about this 1 byte at a time type thing. So, and this is the device itself, not our module. Okay, so when we register a character device, we use this function, register chr dev, and this guy takes in the major number for it. So like last time we saw SDA1, SDA2, SDA3. So that 1, that 2, that 3, those are the in case you have replicas of the same kind of hardware and you need to individually, that's what that major thing is. The name would be like the SDA part. And then we have this file operations struct. Do we talk about structs yet? Did we do them in the 300 class? What's a struct? No. Let's see. Everybody in here has had Python, right? Okay. In Python, what is a dictionary? Okay, so it's a collection of name value pairs. So that's what a dictionary is. So a struct in C/C++ is basically the same thing. It is differentiated from a class in that it does not have functions/methods. Although there is sort of a hack, and you're actually going to see that when we look at some of the sample code here in a few minutes. Now, kind of an interesting piece of information. So C and C++ have structs. Java removed structs. C# brought them back. Anybody know why? I usually talk about this in the when we start making the step towards object-oriented programming. So Java, is it reasonable? Here, I'm going to put this on a different slide. Struct == class without methods. So if you wrote a class and you happen to not put methods in there and it just had fields, isn't that a collection of name value pairs? So then the question is a struct equivalent to a class without methods? We can say this is almost the same thing, but instances of classes, so objects, are passed by reference or value. If we have an instance of some class, like the person class, so I have person P1 = new person, and I pass P1 to a function, is that passed by value or is it passed by address? If I make changes to that person object, so if I create person P1 = new person, we'll just pretend like it takes in a person's name. And then we'll say change name, passing it P1 with the expectation that they'll change the name of the person inside of P1. Will that change be permanent? Yeah. So instances of classes are passed by reference, or we say address. So that's that example. When I first teach about that, a lot of times they'll say something along the lines of, if you go and spray paint my garage, I'll get home, you went to my actual address and spray painted my garage, so any changes that happen there, I'll notice. Whereas if somebody, like integers, primitive types are passed by value, right? If you come up to me and ask for a quarter and I give you a copy of a quarter I have, so let's say I have a couple of quarters, I hand you a quarter and it's an identical copy to the other quarter I have, anything you do to the quarter I gave you will have no impact on the original, right? Because you got a copy. That's passed by value. So structs are passed by value by default. In a language like C, we could pass them by address because we have a special syntax for working with pointers in C. So we can force them to be passed by address using that syntax. But by default, if we just send a struct into a function, it's passed by value. So with that in mind, it is not fair to say that structs are the exact same thing as classes without methods. That's not completely accurate, because they do behave slightly different when you pass them to a function. Now, if you never make changes to them inside of a function, no big deal, right? You're fine. But if you try to make a change to a struct and you expected that change to be permanent, you're going to be in for a surprise. Similarly, if you had passed in a class and you made a change to the class expecting that change to not be permanent, you're going to be in for a surprise. So this is one of those things that is a little bit of a nuanced reality with programming where you can run into problems if you don't really know how it works. So Java's perspective on this saying that, oh, well, we don't need structs because a struct is a class without methods. That's not a true statement, right? It's close, probably good enough for most circumstances as long as you're careful. Can you pass an instance of an object in Java by value? It's more of a trivia thing. Can you pass an instance of an object in Java by value? I mentioned that by default, they're passed by address. What do you think? What's your guess? How? How do you send a copy?
Isn't there like a method to make a copy of that?
Yeah, it's called clone. Yeah, the top level object class comes with a function called clone, which literally just duplicates the memory and gives you a new pointer, a new memory address. It says here's another object. It's the same thing as the other memory, except this guy points to different memory. You change this, it won't break this. Something like that. All right, so we can use the clone method provided by the top level object. All right, so bottom line is you are not actually restricted as long as you know what you're doing, right? If you know that structs are passed a certain way, you can, if in Java, if you pass the clone of an instance of a class, it'll act like a struct, right? But you're having to purposely clone it as opposed to its default behavior working a certain way. All right. So we're not going to necessarily say that this is something broken with Java, but evidence would suggest since C# brought structs back, there must be some value in having this idea of a struct. In general, I mean, structs were the predecessor or the precursor to classes. So structs were kind of where we started hitting our wall in the C programming language. Okay. Dr. Wall, that is. You guys made the science, right? All right, so that's where we started hitting our wall in C, where we really wanted to have functions and stuff embedded inside of these structs, but it was kind of a hack to make that work. So that's where this idea of object-oriented languages came from, where we needed this new layer that I referred to it as kind of like Tupperware, right? You know, it's an organizational method with classes. Okay. So when we register a character device, we're passing it an integer, a string, that's what this char pointer is. So char pointers are strings. And then we're passing it a struct. Okay, and a struct is like a dictionary in Python. It's a collection of name value pairs, which is passed by value by default. Notice here though, This guy has a little star after it. So I'm actually passing it the address of this. Well, this is the function header. So this function is expecting you to give him an int. He's expecting you to give him a string, the character pointer that points to the beginning of the string. And he's expecting you to give him a struct pointer, okay, a file operations pointer. Okay, which means that if you make a change, the change is permanent because you're changing it in the actual place in memory. So this guy takes the pointer to a struct, not a struct. Make sense? So we're forcing this struct to be passed by address when we send it to this guy. All right. Now, before we get too far into this, we definitely dealt with this syntax in 300. Would it be beneficial to do a quick refresher on the star and ampersand address, non-address thing? That'd be helpful. We can do it just in a single like C hello world-y type program real quick. All right, so let's do that real quick. Let's throw it into a slide and then we'll just go and kind of experience it. Otherwise, I think some of the syntax, the code might be difficult to read. If there's just ampersands and stars all over the place, you don't really know what that is. We might get lost pretty quick. So pointers in C, which is the same as in C++. So if you had the 300 class with me, where we use C++, this should be review, but we do have a couple of people from Ann Arbor who maybe had a class in a different language or something like that. And we all probably can use a refresh. So in C/C++, we have a special syntax for dealing with pointers. The asterisk says give me the value that lives at a memory address. Ampersand says, give me the address where a variable lives. All right, so we have these two different little symbols that are used to differentiate between decoding the value added address versus working with the address itself. All right, so let's go look at, do I have Ubuntu loaded on here right now? Yeah, we can just look at it here real quick. So we'll just write a little pointer dealio. I'll tell you what, Visual Studio Code hates coming back to life after you've put like Ubuntu to sleep. Really seems to be poorly written. I mean, it's bad. So just Slack is just broken in it. It's perpetually broken on Linux, it seems like, which actually surprises me. Just update it on here. If you haven't done this before, built into Ubuntu is this thing called apt-get, which is a package manager. So I'm running this as super user using apt-get to install Slack desktop. I assume that's the name of the program. So now when I open this, hopefully it's a newer version of Slack. Oh, it detected a problem. Well, whatever. We gave it the old college try. Well, let's go in here. And I'm gonna steal this one. Yeah, this will work. All right, so this is just a C program. So we're using old school standard IO.H instead of when you had the 300 class with me, we did C++ and we used IOStream. Remember IOStream? All right, so we're gonna go ahead and we're gonna test this a little bit. So I'm gonna create an integer A set equal to 5. Then I'm gonna create an int pointer. I'll call it A pointer is equal to the address of A. Then we're going to create a int B, and this guy is going to be equal to the value that lives at a pointer. And then we'll say int pointer B pointer is equal to the address of B. And then we'll say int C is equal to, well, actually, that'll just be good enough. So we'll say A is equal to %D. A pointer is equal to %P. I'll kick it down a line now. B is equal to %D. And B pointer is equal to %P. %P is a placeholder for pointer, %D is a placeholder for decimal integer values. All right, so we'll go ahead and say A pointer, B pointer. All right, we'll go ahead and save that. So I originally defined A to be a 5. So when I print out the value of A holds an integer. So that's going to print out a 5. When I print out the value of A pointer is the address where the variable A lives. So this tells us where in memory is that 5 stored. Okay, that ampersand gives us the address of the variable A, which we could say is the address of where that 5 lives in memory. Okay, so that'll give us some weird memory address. B, we're saying, int B, is the value that lives at the address A pointer. Okay, so this says go to this memory address and give me the value you found there. Not the memory address itself, but the value you found at that memory address. So this should also be a 5. B pointer is going to be the address of B, which is actually B, yeah, the address of B. So B is an int variable. The address of B is where B lives in memory. And I'm storing the place where B lives in memory inside of a variable capable of holding an integer pointer. So this will be a memory address as well. All right, but the memory address of B, so B pointer and A pointer will be different addresses. Because B pointer is the address of this memory location. A pointer is the address of this memory location. 2 separate memory locations for 2 separate variables. That's the idea. Variables a name value pair, we put them in separate places in memory. All right, but we're holding the same values at both of those memory locations. So I'll go ahead and compile this. What folder was this in? Looks like it's in the 300 folder. What was it? It's hello world.c. All right, so notice 2 different memory addresses. They happen to be very close to each other. They're one integer apart, 4 bytes apart. So they are close. Just happened to be how the operating system handed out to this, because we only have 2 variables. All right, but A and B, the values at those memory addresses are the same value, but this 5 is stored in a different place than this 5. All right, that makes some sense? All right, so that's our refresher for this pointer syntax in C. When you see a star, we're talking about the value that lives there if it's on the right-hand side. So when we said star a pointer, this says, give me the value found at this address. When I say int star, I'm saying this is a variable capable of holding an address. So remember, variables, we have the type followed by the variable name followed by the value. The type of this variable, the type of B pointer, is an int pointer. That is a variable that knows how to hold an address of an integer. Okay, so this star right here, this is actually part of the type. Something that you probably remember me saying maybe in 300 is, I do not like that syntax, which you maybe will see pretty often. That is allowed. When I think of a type, I think of it all being together, right? The type of this variable is an int pointer. I think of that as being kind of like one word, even though technically it doesn't have to be, right? Because int is a type and a pointer is a type, is a generic type. Therefore, an int pointer are 2 separate things that equal one idea. But I think it makes sense to put them together and say, look, this thing is of type int pointer. All right, so pick your poison, I guess, but the reality is you will find that syntax that looks like that. I find too often. I think it's just bad syntax. I mean, I'm never going to take points off for it, but you know, you get the idea. All right, questions about this? Does this get us in the right ballpark? Okay. So let's get back over here. Okay, so again, the function for register character device expects 3 inputs. They want us to pass it a integer, a string, a char pointer. So it's a char pointer because we want the address to where the string begins, right? So strings are represented in C as character pointers. Yeah, see, they even did it right here. Char space pointer. I hate that. And then the last thing we're taking in is a file operations pointer. File operations is a structure. It's a struct type. So somewhere, somebody, which we're going to see on the next slide, has written, and it's a scary struct too, has written a struct called file operations. And this guy is expecting us to pass it called a filled out struct. And that'll make sense when we get to the next slide here. A filled out struct, but a pointer to that file operations struct. So if you think of, since a struct is a collection of name value pairs, you go to the doctor's office, they hand you that form, it says, you fill this out the best you can, right? That's effectively what they're asking for here. They're asking for you to take this struct and put in as much of the data that makes sense for your driver and hand them back the address to it so that they can use that for doing the module registration thingy. Make some sense? That's a good analogy. That's a star for the day. Right, Proctor? All right. So that's the idea. That's where that pointer thing comes in. But if it were me, there would not be a space here. But again, structs by default are passed by value. So in this particular case, we're saying, well, the presumption would be that the character, the registered char dev, might make changes to this struct, or at least has the right to. Okay. Actually, what's funny about that is it is coming in as a constant, which means that it probably wouldn't make changes to it. So then the question is why is it sending it as a pointer? What do you think the reason is? It's coming in as a constant, which implies that it is not something that's changeable. We've filled out the form of the doctor's office in Sharpie. Okay, why do you think it's passing a pointer instead of just the struct by itself? We're making changes, doesn't make a difference. So that's what this struct looks like. We'll walk through this, well, somewhat. Space. How big is a memory address? 32 bits or 64 bits, depending on whether we're on a 32 or 64-bit operating system. How big is that struct? Bigger than that, it seems like. It certainly looks like it should be. I mean, if we just go down the list, we have these are other struct types, right? Then we have 3 ints, we have some long. So I mean, here we've covered 64 bits just in these 2 entries, right? 2 integers, each are 32 bits. So we're at 64 bits. We're at the maximum memory address size just from these 2 entries right here. Yep. Yep. Which isn't a big deal. I mean, you can, in Python, you can have a dictionary that holds dictionaries. Yeah, so I mean, structs just feel scary. Anything with C feels scary because it kind of feels, like you're like in an antique shop, right? But in many ways, I think it's actually better. It explains things better. It shows you what's under the hood. You know what's memory, you know what's not memory. It just feels cryptic, and part of it is because you learn to program in a much newer language. And I see it on the flip side. I learned to program in a language like this, but I've been teaching the newer languages for so long that when I dive back into an older language, I have to kind of readapt. So somebody will see me sit there and I have to screw with something 3 or 4 times before it finally clicks back into C gear. Because I mean, I started writing C when I was like 9. But that was normal. I mean, that was the language then. I mean, Java wasn't a thing. So C++ was a thing. But in any case, so this is this file operations struct. So as we look at this, we're at a 2, right? Not 150? Okay, 2, good. So as we look at this file operations struct, I really like that. I mean, if I do say so myself, I like that idea of that form at the doctor's office. All right, so they're handing you this form. They want you to fill in as much of this information as possible. And some of these things are, so let's kind of walk through and understand at the high level what we're looking at here. So this file operations struct, the first thing it wants to know is it wants to know who the owner is. And there is something called a module. It's just a struct module that we will look at, but we can imagine that's another little form that has the information about about this particular module. So it probably has like the name of the module, a couple other things, right? All right, so here's like a subform. And then we have a file. So here's a struct called the file, which probably has the name of the file, the path to the file, things like that built into it. Here's another file, here's another file. So this is our ability to read or ability to write. This is an iterative read, which I think reads 1 line at a time, but don't quote me on that right now. We'll go through each of these when we kind of have them in an example. Here's another file, another file, another file, another file, another file, another file. So you can think of these as file objects. Because remember, in C, this predates the idea of an object. Or a file object, it might have, you have the name of the file, you have the full path of the file, maybe you have the privileges on the file, read, write, execute, whatever, things like that. So you have information about a particular file, and that is housed inside of this single variable of type struct. That makes sense? Rather than having, if you instead exploded this out and every single time you saw a struct here, it instead was 3 individual variables inside the top level thing, that would start becoming pretty unwieldy pretty quickly. Then you're wondering, okay, well, this is the name of a file, but is this the name of the read file or the write file? So you kind of see the purpose of having structs within structs. I mean, it's an organizational thing, just with objects. All right, so you're passing it pointers to a bunch of files. And then these are more OS related things. Here's locks, here's sync stuff, flag check stuff at the OS level, splice read and write. I don't remember or even know what some of these will do. We'll look them up when we get to them. But punchline for us looking at this, we can see that this file operation struct we're giving it is something that certainly for us, when we write a fairly simple driver at first, we're probably not going to fill this thing out very much. We're going to kind of give it the bare minimum, right? All right, but the point is that if we are writing something very complex, remember this module ability is something that would allow you to do anything from a useless driver all the way up to, you know, something very proprietary for maybe talking to a, you know, some crazy piece of equipment or something like that, that, you know, some company made and has a proprietary driver for it. So it needs to give you the power to accomplish a lot, even though depending on what you're writing something for, maybe you're writing a driver for a mouse, you know, which is pretty simple. Maybe it's just a 2-button mouse. Doesn't even have the scroll wheel, right? You know, then maybe that driver is going to be pretty simple and you're not going to use all this stuff. Go ahead.
Like a higher level, is each individual element in the struct a module, or is the whole piece here?
Well, the only thing that's actually a module here is this top struct owner. So this whole thing is a thing called file operations. And one of the things it takes is it needs to know it has module information, who owns this module. And at some point we'll look at this struct. But then, you know, each of these is a potentially useful piece of information related to the file operations, related to this file and /dev, which is a character device that we're registering. Remember from the previous slide, that whole big thing, this is that form right here. It's the third parameter we're passing to our register character device. So register character device will make something show up in the /dev folder as a device that we can read and read characters from or write characters to. And so this is the name of it. This is the major number of it. This guy is kind of like the contract or the details of what's allowed, what's not allowed. When you read something from it, where does it actually come from? That kind of stuff, because those are all in that file operations struct that we're passing it. And we see a simple example here coming up. All right, so we can appreciate that this is a complexy thing that probably weighs a little bit if we were to pass this thing by value. So that's why we pass the address of it. Okay, so here is an example of a file operation. So here's a simple driver file operation. And this is of type struct file operations. So this is a variable of the same type as this guy. But notice, so we have in here, we have something called owner. So we have owner, and presumably there's a variable defined higher up in the code called this module, right? That is of type module struct, okay? And then we have a read. So here's our read right here, which is going to be a file struct. And this is our device file read, presumably another variable defined up top, right? So we have two different variables that, you know, are higher up in our program. One was defined as a struct module. The other one was defined as a file, a struct file. So C is kind of weird where you always have to put, typically when we define a variable, we put the type, then the name, and then the potentially the value. With structs, you always have to put the word struct in there as well. So it's struct type name instead of just type name. Make sense? So you kind of have to flag it as struct. That would be something just left over from compilers in the early days, let's say. Okay. So here's our device file read, which is going to be a function that we would have read. So the declaration of this module macro is contained in, oh, so it's actually a global variable. So this module is the module we're currently writing. It's kind of like the keyword this in Java, saying, hey, this is the module we're doing is me. It's this one, this module. So that's in Linux export.h. And then this is the method header for device file read. So this is called prototyping a function. So they're passing that function that we've prototyped, and it happens to be a function that takes in a file pointer, a size struct, which is probably just an int type, and then this other type. Typically, things that have an underscore T on them are structure types. If you have variable names that have an underscore T, or if you have types that have an underscore T, it's probably a struct. All right, so right here it's just saying this is the name of a function that we intend to write later, but it will make this line legal. All right, so we've only filled out a very small portion of that file operations thing. Make some sense? Okay, so no homework for Friday. There'll probably be something over the weekend, presuming we can get the virtual machine going. So that's my goal for Friday, is I'd like to type some of this in class and see some stuff happen. But worst case is we're going to keep going down this thing and kind of see how this all comes together. So kind of see what we're supposed to do and then actually do it. Cool? Questions, comments, concerns, bribes? Go ahead.
I have a question just about like the kernel. It was interesting that I was researching like Linux kernel modules. They were saying it had a monolithic kernel as opposed to a microkernel.
Yeah.
And I know there's like a difference between them, but like what's the
Yeah, so part of that is the popularity of Linux. So Linux in the early days was a monolithic kernel because it was built off of Unix. Now, the question would be, is at what point do we consider something a microkernel versus not a microkernel? Linux's kernel is smaller relatively today than it was in the beginning because we've pieced out these module things. So with the idea of it being a modular kernel, I would call it an overweight microkernel, is what I would call it, because it has removed elements that are external to the actual kernel into these module things. So that's the concept of a microkernel. Microkernel doesn't really dictate how much does it actually weigh, right? So really what you were reading is kind of the Linux kernel is pretty bloated because of it's an open source project and the number of people that are working on it. So it supports like 30 different file systems that are experimental and things like that. It's an interesting project, but it's somewhat of a Frankenstein. All right, cool.
Is Linux unique in that way then? So like Windows and Mac OS aren't considered microkernels?
Well, they would be, I guess I don't necessarily know this for sure, but I'd be very surprised if they're not very similar to Linux. Because the developers who are working on Windows, every single time they add something, when you're going to patch Windows, you don't want to have a brand new kernel installed. You want to have modules that plug into the kernel. So this concept of a microkernel, as long as you kind of squint a little bit at the word micro, I think is pretty much the way operating systems are done today, is having them be modular like that. The uniqueness to Linux would be that you have a public community working on the kernel, whereas Windows and Mac OS, you only have the Microsoft and the Apple people working on it. So presumably it's a little bit more focused, because you probably have people with the Linux community who have their like pet projects, adding, like a good example would be adding NTFS support to Linux way back when. That was considered very experimental and kind of dangerous to read your NTFS file partitions from a Windows XP machine or something like that. You could read it, but you couldn't write it because it might get corrupted. So that was like somebody's pet project for a long time. And how many other projects sort of kind of like that exist? That is unique to Linux, where, I don't think you just have some crew over at Microsoft who's decided they want to embed something like that into it. Cool?
Cool.
All right, what's up?
You know, one more.
Nope. Right there?
Or the one word have
Oh, this guy?
How do you read?
How do you read this?
Yeah, like, when you're looking at and I like a serial declaration or like when you're doing like a model.
Well, this is the definition of the struct. You fill it out like we did here in this very simplified version of it. Yeah, so this is us actually creating a variable called simple driver fops for file operations struct. So this is how you implement it if you're not going to fill out the whole form. But we'll see a real example once we get into it. But this is like a much more realistic example than filling out the whole thing.